Hello, welcome to Old Morgan Labs, and today we'll be talking about atmospheric thermodynamics. We're going to find the temperature of an air parcel. This is a common problem people use when they study meteorology, oceanography, weather, things like that. It's different from mechanical thermodynamics. But anyway, similar enough. We have an unsaturated parcel at 1 degree at 980 hectopascals. It's raised adiabatically to 700 hectopascals, then sinks dry adiabatically to 1000 hectopascals. So you have a patch of air that's moving up and down in the atmosphere, and the altitude is basically your pressure. Okay? We want to find the temperature at A, 700 hectopascals, B, 1000 hectopascals, and C, potential temperature theta. So for part A, finding the temperature at 700 hectopascals, we use the lapse rate for dry, unsaturated air. That's the key that makes it simple. We have unsaturated, dry air, and it's adiabatic, so there's no big heat being added. It's dry, so there's no water vapor being added. This is like simple hand calc that you can do. But we're given pressures, right? We're not given altitudes. So what you have to do is convert your altitude, your 1,000 meters, to pressure. So we have this 12 hectopascal per 100 meter conversion. That's like a lapse rate in terms of pressure. Okay, and we can use this conversion all the way up to 20 hectopascals. That's the upper atmosphere. The curve kind of levels out when you get up to those upper atmosphere altitudes. Okay, anyway, so you see down here we have 10 degrees C over 1,000 meters. We multiply that by 100 meters over 12 hectopascals. You see in the red our masses cancel out. We cancel out the two zeros here. We cancel out another zero from the 10 and another zero from the 100. So all that, in the end, we get 1 degree per 12 hectopascals. That's all we want. So to continue part A, now we have our lapse rate in terms of pressures for dry air. I keep saying dry air. This is the assumption that you have to make it simple. Okay, delta P is final minus initial, right? All deltas are final minus initial. So our final is 700 minus 980 is our initial. So we have a negative 280 hectopascal delta P. Now to find our delta T, we use 1 degree Celsius over 12 hectopascals times negative 280 hectopascals, which equals negative 23.3 degrees C. That's our delta T. So we start out at 1 degree. So if our delta T is minus 23.3, our answer would be negative 22.3 degrees C. So that's A. Done. Now for B. B is going to be very similar. Since it's adiabatic, unsaturated dry air, you just keep using the lapse rate. Okay? This is just a simple problem so you can understand the more complex stuff. Alright, so now we're going to find the temperature at 1000 hectopascals. Our lapse rate is 1 degree per 12 hectopascals. Delta P here would be 1000 minus 980, okay, equals 20 hectopascals. Plug that all in. Delta T comes out to be plus 1.67 C. So we started out at 1 degree C, and our delta T is 1.67 degrees C. So our temperature at 1000 hectopascals is 2.67 degrees C. We could have picked the 700 for our final and used our temperature from part A, but I think this is simpler. Now, part C, finding the potential temperature theta. For this, we have to use our equation theta equals temperature times P naught, which is our standard reference temperature of 1000 hectopascals, over P, raised to the R over CP. Okay, here are all our pieces to this puzzle here. Before we calculate it, potential temperature is kind of like a gauge if your air is stable or not. Almost like if you've taken fluid mechanics and you have the Reynolds number. If you know your Reynolds number is a certain value, you know you have turbulent air. Okay, this is kind of a similar thing. It tells you if your air is stable or not, how stable it is. Okay, so now you know kind of how you're going to use it. Let's calculate it. Okay, now we have, okay, so R for air is 287 joules per kilogram. Our CP, we have to find a chart and get CP at 1 degree Celsius. And after we do that, we find that it's 1.004 joules per gram K. Now we have to do a little math here because the units, in order to work them out, you have to have joules per kilogram. So you just multiply the chart value by 1,000 to get 1,004. All right, so you skip down over here and you get the R over CP is 0.286 or 2 over 7. Okay, you may see that in your textbook. K is 2 over 7. All right, so our P is 980 hectopascals. Our temperature is 1 degree. For this equation, you have to convert your temperature to absolute. So absolute is Kelvin in the metric system. So we have 274.15 is our temperature. So we go over here, plug everything in, we get 276.1 degree K, which is 2.9 degrees C. And that's our potential temperature. Now, a side note, we could use any pairing of pressure and temperature that we found, okay? Since it's adiabatic, we don't have any air coming in, or not air, but water vapor. We don't have any water vapor mixing in as it's rising or falling. We don't have any heating as it's rising or falling because we say adiabatic. So we can use, in this case, you could use any one of the 3 states, pressure and temperatures, and you'll get the same potential temperature. That goes back to what I was telling you about stability. It tells you the stability. Okay, that's it, A, B, and C. So as a bonus, if you want to keep looking, keep watching, here is the table, okay, for your specific heats at constant pressure, your CP. As you see here, I saw CP at 250 and CP at 300. And in my calculator, my TI-85, I used the interpolation function to find that. All right, so if you don't know how to do that, or if you have a TI-84 calculator, you can go to my tutorial GCT001 or GCT002 to figure out how to do interpolations. All right, that's it. Hope you learned something. Leave comments below and subscribe. Thanks a lot.